note, start recording. Administrative stuff. I'm sure a lot of you have seen that I extended assignment 4. I mentioned on Thursday that I was probably going to do it just so we could space it out better with the exam. So that's extended to either Thursday or Friday, maybe even later. I don't remember where I extended it to exactly. And then I extended assignment 5 as well, although that's still a little while away. Another thing that I've had written down for a little bit is a student had asked me if I could do a solution to assignment 3. So I will likely do a stream for that, not on a class day, but just at a different time, probably over the weekend, maybe next week, where I just try to program assignment 3 and just take any questions if people had it. That way everybody can kind of see maybe how you could program it kind of efficiently, and if you were stuck on it, just get some idea of what you could have done to solve it. So I'll make an announcement about that at some point, but just so that everybody's aware, we'll probably do that via WebEx, and then I'll record it and upload it at some point. I think that's it for administrative stuff. Does anybody have any questions with regards to assignment 4 so far? Okay, don't see any questions, but if you have any, feel free to stop me. Today, I just wanted to take a little bit more time to talk about pointers in more detail and kind of how they work with classes a little bit, and just get an idea of how we can traverse things using pointers and do some weird stuff. And then I'd also like to talk a little bit about static scope and just go over that in more detail. And then if we have some time, I'm trying not to get too ahead because I know that the Monday, Wednesday sections are a little bit behind because there was a holiday. But if we have time, I guess we'll start talking about the next topic in the syllabus. And we are a little bit ahead, so I'm trying to spend some more time doing review, if possible. But anyways, you can see I have just a wall of comments here. We don't have to worry about these too much. I'm pretty much going to talk about all this anyways. But what I want to do is I want to go through how we can access things in a class object, knowing what the class is, and access those members, and then maybe talk a little bit about the applications outside of this. We won't go into a whole lot of details about the applications because I think that's more applicable to classes that are supposed to be more technical than this one, whereas I think this class is more about programming. But we'll still take a look at just how things are laid out and what a class looks like. But I have a class here. It's called the container, and I just picked a random name. And it contains an integer, a character, a string, and a character that are all private members. And I just declared them in this specific order. And this will actually end up being important, the order that I declared it in. So we'll see a little bit more as we go on with this. And then I just have a constructor here. And the constructor just takes an integer and a string, and then the two characters I just hard-coded to be the literal C, like the actual character C, and then the actual character D. But we have this order here that it's the integer, it's the character, the string, and then the character. And then in my main, all I really do is I construct it so that the integer is going to be 5 and the string is going to be hello. And then the rest of the code we'll get to, but before we start looking at this, I want to talk about why these are in this specific order and what it means when we do that. When we do a class declaration, we know that it represents some kind of blueprint. It tells the compiler, this is what this new data type that I want to exist means, and this is what it contains. So when I write class container, integer I, make that look a little nicer, integer I, character C, string S, and character D. What this says is that we are going to create objects with this type, and every time we make one, it's going to have all of these members, assuming that they're non-static, which we'll get to in a little bit. And so that both effects like our actual coding, when I make actual variables, let's just say containers C, I can access them with the dot operator, right? We can do c.c or c.s or whatever to access the actual members. But it also, because it's a blueprint, dictates the way that these are stored in memory whenever we create one. When I do a variable declaration or anything that creates a container object, then it needs to know how to put it in memory, and the way that it knows to do that is based directly on the blueprint that we give it, the class declaration. So when I do that variable declaration that I wrote below, it goes into memory, keeps a pointer to it, which we don't necessarily need to know, but you'll see my code up above is going to do it, or my code over in Visual Studio is going to do it, and it allocates all that stuff. So it allocates it specifically in the order that you write members. And there's a little bit of some differences here in the way things are handled, but generally it's going to do the integer first, and then the character next, and then the string, and then the character afterwards. And I've made these different sizes because all of these data types are different sizes. We've talked about this a little bit previously, and you don't need to know it for the sake of this class, but I'll just throw it out there anyways, that an integer is 4 bytes, a character is 1 byte, a string is either 8 or variable, kind of depends on how you frame the way that works. We're going to take a closer look at it here. And we have some other things, like a double is 4 bytes, or sorry, a float is 4 bytes, and a double and a long are 8 bytes. And a Boolean is 1 byte as well. But for the sake of our example, these are what we have. So this is why I've drawn them in different sizes. When I write this integer here, it's taking up 4 bytes of memory. This character is taking up only 1. This string is probably taking up 8. You'll see it's a little bit weird. I messed around with it earlier. I'm not entirely sure why it does things strangely. But we have this last one that is also a character, and so that's going to take up 1 byte. This is 1. This one is 8, which I don't even think I drew 8 correctly. 1, 2, 3, 4, 5, 6, 7, 8. Totally not to scale, but that's all right. We got a 1 here, and this one is 4. So the blueprint for a container, the class declaration, says that the first 4 bytes are the integer I, the next byte is the character C, the next 8 bytes are the pointer to string S, and the next byte after that is the letter D. And because of that, we can actually access each of these members if we just use a pointer to this object and kind of traverse it straight from the top downwards. And so I want to do that in our code here and talk a little bit more about the way strings are implemented. You're going to see, I tried to print it. I don't know if it's just a Visual Studio thing or if C does it strangely. I was trying to find more information, but I couldn't. The string is going to be printed a little strange, but everything else should be kind of what we expect. So we said I was first, C, S, and D. And what I have here in main is I make a void pointer. If you remember, a void pointer is just a pointer that doesn't have any inherent type, meaning it just keeps the address of the thing, but it doesn't know what's there. And that's totally fine for the sake of our problem. We'll figure out what's there later. But I keep a void pointer to a instance. So I instantiate a container here, and then I keep track of the instance in our void pointer. And all this is going to do with this constructor is it's going to set I equal to 5 and S equal to hello, which is not important. I'm just doing that so that we can see it as we print out. But anyways, we keep that pointer. In the context of my drawing here, that's just this C. It's a pointer to the top. Remember that when we do pointers, it always points to the top of wherever all of our stuff is allocated. That could be with an array, it points to the first element in the array. Or when we're doing objects like this, class objects, it points to where the beginning of all this stuff is that has some sort of blueprint as to how to make it. Now, after that, I do a integer pointer called container int pointer that is just the same pointer, C here at the top. I'm just going to point to that and then cast it to an integer pointer. And all that means is I'm going to look at the top thing, and rather than saying it has no defined type being a void pointer, I'm going to say, let's try to treat the beginning of this object as an integer. And then I print that. I dereference it and I print it. So let's take a look at that really quick first off. And when we run it, we get some more stuff because I've programmed stuff beyond this. But you see we get the number 5. And that's the first thing that gets printed. So if I go to the location where this object is stored and try to print it as an integer, because there's an integer at the top, it's able to print that integer. If I was to try to print it as like a container object, well, then that's not really clear because we don't have an operator overload. But if I was trying to print it as like a character, then it would be some unintelligible garbage being specifically the first byte of this object. So if I was to try to print C as a character pointer, so I cast it to a character pointer and then try to dereference that, it's going to mean just this part here, because a character we said is 1 byte. Then when I cast things to a different kind of pointer, it tells me how to interpret that data. And that's why I can have a pointer to C, which represents a container object, and then tell it to print it as an integer pointer. So do it as an integer pointer, and it will only grab the next 4 bytes because it knows 4 bytes is an integer. And that's why we get the number 5, is it's pointing to the same place as the integer, and the casting part tells it that's how to interpret it. Any questions so far on that? I think the key takeaways being the fact that everything is stored right next to each other when we create a class object in the order that you declare it, and that the pointer type just tells you how to interpret that data that it's pointing at. But is that clear, or any questions about that so far? Okay, don't see any questions yet, but fair enough. If you have any, just let me know. Right, so let's just go on with the rest of the code I wrote here. What I do after that is, we know that this was pointing at the integer. We had a pointer to the top called container int pointer, and then I'm going to add 1 to it and change it to a character pointer. So what this does is, if I add 1 to it, this again depends on the kind of pointer that we're dealing with. I'll move this up a little bit. Actually, let's just draw a separate example off to the side here. So we know I is here. I is 4 bytes. And then we have C afterwards, which is only 1 byte. Right, and then we have a pointer to the top. Let's just say we have a void pointer called C that points to it. Assuming I have the container already. And then I made an integer pointer. I'll just call I pointer, I guess, for the sake of our example here. And that was just the void pointer casted to an integer pointer. Now, when I do I pointer plus 1, does anybody know? I should probably move it up a little bit. When I do I pointer plus 1, assuming that I pointer is right here, does anybody know where that ends up? And I'm just going to label this a little bit. This is 0, 1, 2, 3, 0 being the top, 1 being this one, 2, 3, I guess this would be 4. Where would I pointer plus 1 end up if I pointer is at 0? Any guesses? So the CPU guess is 1, which I think makes sense. But it's actually not how pointers work. So fair guess is that it would end up here. It would just move up 1, which I think is intuitive. But actually, when you do addition with pointers, it's based off the type of the pointer that you're dealing with. So I'm going to do 2 examples here. I'll do I pointer plus 1, and then we know that V is pointing to the same place, or sorry, C is pointing to the same place, which is hex 0. If I did C plus 1, that is actually what you're expecting. More than likely. I think the way void pointers work, that's fine. The I pointer plus 1 actually ends up at 4. Does anybody have a guess as to why it ends up at 4 versus the other one? So I'm technically adding 1 to both. Why do they behave differently? And maybe I'll direct you to the key difference between these two, because they're pointing to the same location, right? They're both pointing to address 0. The difference comes in the type of things these are. So this one's a void pointer and an integer pointer. When it's a void pointer, by definition, it's going to work on a byte level. When we do an integer pointer, it works on an integer level. And if you remember from earlier, we mentioned that an integer was 4 bytes. So when we actually do this, it's going to jump forward by 4 bytes when we do an integer addition. So when you do addition with pointers, it's not moving forward that many bytes, but rather moving forward that many blocks of whatever you're talking about. In this case, because we have an integer, it moves forward past one integer, which is 4 bytes. So by doing plus 1, I end up on the other side of I, rather than just in the middle of I, if that makes sense. Any questions on that specific part, or is it clear why the addition ends up at 4 here versus at 1? And why it would end up at 1 if it's a void pointer? Okay, don't see any questions, so we'll keep going, but if you have any later, just let me know. But this is why in my code I've done plus 1. See here that I've done a plus 1 to the integer pointer, which is going to move it forward past that integer I in our memory, and then it's going to end up on the other side. So here I'm adding 1 integer rather than adding 1 byte. What I do after that is I just kind of arbitrarily picked 20. And what I do is I'm going to print the next 20 bytes after that integer. So if we go back to our picture here, then, the picture we had earlier, then we know that after the integer, there's going to be the character C, this string, and then D. What we should actually expect is not for the string S to show up, hello, but we're going to see it anyways, and I'm not entirely sure why that is. Actually, so I ran this earlier. You'll see that it prints the 5, it prints what appears to be a line feed, or maybe I put that in there, and then it prints the C, which makes sense, right? After the I, we expect the character C to be there, and then we expect it to print the string. But for whatever reason, it prints this garbage. 1, 2, 3, 4, 5, 6, 7, 8, 9, about 9 things. I would assume 8. I'm not entirely sure why this is here. And then it actually prints hello. And then it goes back to printing just garbage here. And then doesn't print D, which is even more strange. So I want to talk a little bit about how a string is actually stored and why we would store it that way. I'm not entirely sure why the D doesn't show up, though, or why there's just random garbage before the hello. But anyways, The way that a string works when you actually allocate it, you've probably seen when you've written command line arguments that a string is a character pointer. Sorry, just had to do something really quick. But a string is a character pointer. And so that means that it's a pointer to an array of characters. And the reason it's done this way, rather than just be its own type, is because a string doesn't really have any defined size like any other thing is. So when I do an integer, that's always 4 bytes, at least on modern hardware, and it should always be 4 bytes. If you've taken CP 100, then you know that there's like a sign bit, usually, if it's an unsigned int, whereas that's a 1 or 0, and then the rest of it's in 2's complement, right? Where we have 31 bits for that. But a string kind of has an issue where it can't necessarily have a defined size because you don't know how many characters are going to be in a string. For instance, if I have the string hello versus the string me, then this one is only 2 bytes long because it only has 2 characters. Realistically, probably 3 bytes because there's usually an extra one at the end to tell it that it's at the end. But this one's 5, right? And so we can't have a defined type because we don't know how long it's going to be. It's a variable length. We don't want to waste extra space by making it something consistent and then having short strings like this waste all the extra space. And we also want to make sure that if we have a really long string that we can fit it. And so strings are a little bit tricky. We don't want to allocate that variable length either. So consider that because a class is a blueprint, this S here, if I made it variable, then every time I do something with that string, all the data that comes after it has to be moved along with it, right? Like if I made this string longer, if I was to do it in an implementation where I just put the string directly into the thing, then this D has to move down. And if there are things following the D, then all of those are going to have to move down as well. And so that becomes really annoying and very inefficient if we try to do that. So instead, the way that strings are implemented is that it will allocate it pretty much dynamically, and then the thing that's kept in the class is just a pointer to that string. So this is why I said it's 8/variable. A pointer is always 8 bytes, and so when we do an allocation of a string object inside of a class, it's going to be 8 bytes because it's going to be a pointer to that object, and then the string is actually located elsewhere. So when I do hello, it's going to be a pointer that is 8 bytes, and then that's just going to point to the array that contains the word hello. This way we can always keep kind of some consistency inside of our classes, make sure that it's always 8 bytes. We don't have to resize anything. We don't have to do anything strange. And whenever we change that string, we can just have it point to wherever the new string is, wherever that array is. And this is just the general implementation of strings. As far as I can tell, C++ does this implementation. It seems to be what I found online. I think that's pretty normal. This is kind of like the standard way to do strings. That's why I'm a little confused as to why we get this random garbage before and after, and not just random garbage and then not hello, is because hello should not actually be stored in the class. It shouldn't be like with this S part that's just a pointer to the word hello. But, you know, I'm not sure. Maybe that's just a Visual Studio thing. On that note, any questions about strings in particular? Does it seem okay that it puts it as a pointer just so it's always consistently the same size, so it's constant? Okay, fair enough. One last note, I guess, just if you wanted to traverse this and not have any knowledge about any of these things, then you could totally keep a void pointer or a character pointer and just use it to traverse the array, or sorry, the class object, and it would go one cell at a time. When you do stuff like that, though, you kind of lose access to what the actual information was. So consider, because this integer is a thing of 4, I could traverse it one block at a time and it would probably just be meaningless garbage, which is why it can be kind of hard if you're playing around without any knowledge of the class to figure out what the data is. This is why a hex editor is pretty helpful. You can usually find information at least via characters because that's kind of like a starting point. But yeah, just something to note is you can traverse this in ways that aren't, the actual block sizes. So I could do this with my void pointer that I had earlier, and it would just count one block at a time and kind of be in the middle of data in kind of just a weird garbage state. I think the last thing I wanted to bring up with this is just why it's important to know this. Even if you decide not to program in C and C++, where you can kind of get away with knowing this and do some stuff to optimize your memory usage, it's still important to know that there are pointers around when you do strings specifically, or when you make a class object, and that they point to areas, and that you're doing your deallocations correctly, because consider the memory is just where everything is stored. It's some big stick of RAM, let's just say, and it contains everything. So when you have memory, not only are your variables inside of this, but if we're talking about the entire memory bank of the computer, then there's also other programs running in there. So their data is also on the memory space. Realistically, you can't access that if you're trying to do a C++ program, because the operating system is going to stop you, but it is there. And the same thing goes for just programs themselves. Programs, like anything else in a computer, have to be binary. In this case, a program is just a collection of binary that tells the CPU this is how to run this specific operation. So, whether that be addition or subtraction or whatever, then there's some sort of binary that represents that. And it's stored in memory along with anything that your program uses. If somebody was to somehow gain access to permissions and override that operating system safety, and then also have access to pointers that you haven't deallocated or fixed in some way in your program, then they have access to other programs that are running on the same computer, the data for those other programs. Even the operating system itself is a program, therefore it has access to that as well. And so it's very important that you try to manage your pointers and be safe with them if you try to do this. So the two things that we've talked about with that is deallocation. So make sure if you're doing C and C++ that you delete things, and that you don't leave any sort of dangling pointers to anything. So remember, we talked about a little bit at the end of last class, if I had an object, let's just say I'll call it O here, and then I deleted it, that you make sure that you set that to null. So when I deallocate, right, it becomes usable again, but you might still be pointing to it. So these two things in particular are pretty important in terms of security things, even though they don't always apply to every programming language. But that's just an aside I wanted to mention as to why we even bother learning this stuff. That being said, being efficient with memory is great, but C and C++ are pretty much the only language. Maybe Rust a little bit is kind of popular now. Yeah, so deleting and setting equal to null is one important thing when you're doing a pointer. If you're done with something, even though it may seem inefficient, go and set your thing to null, or it might seem tedious. Always set pointers that you're done working with to null, and make sure that you're also deleting things that you're done using anyways, just on top of that. Those two things are super important on top of the memory leak stuff we talked about, because those can lead to vulnerabilities in certain programs, and you really want to avoid that if possible. And again, this stuff won't, the last part here about this being like security vulnerabilities won't be on the test, just something to consider for future classes. But yeah, definitely set to null whenever you're done with something. Don't just leave it there, and also don't just leave the memory there. Cool. Any last questions about pointers or memory before we start talking about something else? Okay. Oh, sorry. One last thing I did want to mention is with this whole class declaration thing, you'll notice I also had a function, a constructor, but that's a function, in my class as well. Any sort of functions, whether they be static or non-static, never are they included in the blueprint. They're allocated and put somewhere else. So there's no extra thing at the bottom of here that determines what the constructor is. It's just your members, just your variables that end up in this allocation. So you don't allocate memory for code. That's just allocated one time when your program loads. It's never part of an object. So that's not included in this. I just wanted to make a note of that. I put that here as a comment. So this constructor doesn't just get tacked on at the end. Okay, so let's move on a little bit. I don't know if I want to do a program for this, but I at least want to talk about static scope a little bit more, because I've been getting some occasional questions about static scope, and I want to talk about it in more detail. We had two different kinds of scopes when we're dealing with classes and structs, which were static scope and non-static scope. And in fact, if something is not in a class or a struct, then it has to be static. But we have a static and a non-static scope. And what a static scope is it only exists once. It exists once, and it's separate from instances. And something that's non-static is something that is tied to an instance and exists for each instance. So rather than existing once, it will exist for multiple things. For example, if I just had an example class here, where we have an integer I, and then let's say a static integer count. And we'll say that I initialize the count to 0 somewhere else. In fact, let's just do it down here. The way, just as a reminder, for static initialization in C++, if you have a static variable, you have to initialize it outside of the class for some reason. And you have to put the type in front of it too, which is weird. So I have to do int count equals 0. I don't know why it does it like this. I assume there's a reason with the compiler, but so I have a count that's static and it's 0 and an integer I. And then let's just say I had a constructor that takes integer I and sets this I equal to I, and then it does count plus plus. We'll go off to the side a little bit more. Hopefully everybody can remember that count is 0. It's not too big of a deal. But I can go and write some code here in my main, let's just say, where I declare a variable called ex, let's say 4, and then I make ex, let's say e2, and I give it a 7. And so this will go and call the constructor, right? And it's going to make two objects, one called e, one called e2, and it's going to set both of their I variables to 4 and 7 respectively. So remember when you instantiate something that it goes and makes like this own thing in a bubble, which we call an object or an instance, and they keep track of their own variables. So for this one, I was 4, and this one, I was 7. When we do something that's marked as static, then it means that it is outside of any instance. It just exists kind of freely, but everything has access to it. So in the example here, we have count. It started at 0, and by doing a count plus plus, I'm able to share this across all objects. So when this goes and instantiates the object e, it sets its variable equal to 4, and the count becomes 1. And when I go and instantiate e2, it sets its I variable to 7 and makes this count equal to 2. So static variables are ones that we're able to access independent of any single object. They just exist kind of free-floating in space. You can tie them to a class so that you can call them via a class name, but they don't exist in any sort of class object. And for the sake of our example, count kind of makes sense for this, right? Because you would want to count all of the objects separate from the objects that actually exist. So no one object should know the count and all the others don't. It should kind of be like a shared thing that all objects of this example class know, right? If I was to make an E3, I wanted to know on top of that what the count is and be able to modify it, right? So a static scope, it exists once, it's outside of any instance, and it's not tied to an instance. Whereas our normal variables, like this I here, are separate and determined based off of a specific instance basis, right? For a more concrete example, maybe I would name this, let me rename this class so that we can kind of get a better idea. Let's say I called this person and then just gave them a name. String name, and then, I don't know, we'll change this to a string really quick. String n, and tie it to that. So we'll just say name equals n. And then change this really quick. Then I think this is a little more analogous to real life. Like every person has their own name or set of attributes that are independent to them. So for instance, I might have a person named John, so J has its own name and D has its own name, being Doe. But we want something to be like shared between them, like the count here. Right. So we've gone over this before, but I just want to expand upon it a little bit. So we know now statics just means that it's able to be shared across everything, and that it's not tied to an instance. We're able to mark functions as static as well, which means that the function is not tied to an instance either. So consider here a constructor can never be non-static. That's kind of one exception. That has to be tied to an instance because a constructor is always called when you instantiate something, so that's just tied to an instance no matter what. But let's just say, I'll write the code over here to the side. I expand upon this a little bit so that I have two functions. Let's just say void print name, that's just going to print the name. We can assume that the code is written here. I'm sure you guys know how that works. We'll just say that. And then I'll do a static function called getCount. I guess that should be an integer. Let's just say it returns the count. So I'm allowed to mark functions as static and non-static as well. And we said earlier that they're stored statically, but that's not a super big deal. But what this allows me to do is I could then call a function like j.printName. And this would presumably, if I've written the code, print the name John, right? And if I did d.printName, it would print the name Doe. And they would be separate. So the thing to consider about this is that this kind of function where we print a name has to be non-static because a name is something that belongs to a specific person. Like I can't just know what a name is without having the person whose name that belongs to, right? So I can't just say, you know, print name without a J or a D in front of it. I couldn't just say print name, because if we consider this from like a real world perspective, this is ambiguous, because it's like print the name of who? What do you mean? So a print name is a non-static function because it has to be tied to an object. It needs to have some sort of instance for it to be able to make sense. On the other hand, getCount, you can use non-statically in C++, but I'm going to say let's don't do that. This is marked as static. So if I went up here and just said get the count, then that doesn't have to rely on knowledge of who John is or who Doe is, right? It just needs to know what the count is, which is like separate and outside of those things, right? So this is valid if something is static, is that it doesn't have to be tied to a specific object. I don't have to have J or have D or any other object to know about something being static. So far, is that clear on the difference between static and non-static in terms of where you would use them? So static being it exists outside of instances, and non-static meaning that it's tied to an instance. Okay, let's keep going then. Again, if you have any questions, just stop me. So we know now, at least as a refresher, static means that it's just free floating. It doesn't belong to any specific instance, so the count here doesn't belong to J or D. And non-static means that it has to belong to a thing. So what I want to talk about a little bit more is what you're allowed to do in static scopes and what you're allowed to do in non-static scopes. So the only time we ever have a non-static scope when we're doing object-oriented programming like this is when we call a function using an instance. And specifically one that's not marked as non-static. C++, again, allows you to use static functions in non-static ways, which I don't think is good practice, and I would encourage you not to do. But if I wanted to print name, then that's the only really way to get something that's non-static. It's tied to an object when we're doing code. If I was to go and write that print name, which is non-static, then we need to consider what we'd have access to. So let's say John calls print name. Out of my variables that I have, name and count, which one of those do you think I should be able to access? Or which ones do you think John should be able to access? So first off, do you think John should be able to grab his name if he's calling a function himself? Do you think he should be able to know about his non-static stuff. Yes, yeah, you're right. You should be able to. So if John does something non-statically that is tied to the fact that he is John, something that only John could do, then he needs to know things that belong to him. So you should have access to those. Right? So the name was a non-static variable, and we are able to access it in a non-static scope, which kind of makes sense. If John does something, then he should be able to access things that belong to him. Now, what about the count? Something that's static. Should John be able to access the count from any of his functions? Any guesses on that one? If not, that's okay. So I see one no and one yes. So actually, yes, yeah, you should be able to. And we gotta consider we actually did this in. I know it's off screen, but we did this in our code a little bit here. We accessed the count in the constructor, and we're able to do this because the count is static. Just consider that what it means to be static is it exists one time. It's not tied to an instance, but instances totally are able to see it. So if we consider this in the context of our problem, John and Doe are both able to see the count of how many people there are, and that's totally okay because the count doesn't need to be tied to any one specific person. We can just know how many people are in a room, let's just say, or in the context of our program, just how many people we've created, and everybody, like, there's no problem with them knowing that, right? They can understand that information, and they don't have to, it's, even though it's not tied to their specific self, it's okay that they know that. So static variables are totally okay to use in a non-static scope because you can see things that are shared in a instance situation. So John is able to see things that are shared between all people, being the count. Again, like static kind of just means that it's shared to some extent. But on the other hand, if we had a static scope, a function which was called from outside. So what did I don't remember what I called it exactly. I would just call it get count. Try to move that down a little bit. I'll try to redraw this so it's a little bit clearer in a second. I know there's a lot of stuff on screen. Then if I was to call a function statically, the get count function, where it's not tied to a specific object, so John's not the one calling get count, Doe is not the one calling get count, it's just kind of this free floating thing. First off, should I be able to get something that's static like the count? If it's static. And I see a yes, and you're definitely right. So we can still access static things from the static scope. Otherwise, our get count function wouldn't work, right? So that's fair. That's right. What about non-static things? So if I was to call this function kind of like nebulously outside here and call the get count function where it doesn't belong to any specific instance, what would happen if I try to access the name? Would it be possible? And if not, why? Okay, yeah, so I see fair. Fair answer. No for that one, and you would be correct. I can do this. So we cannot access non-static things from a static scope. Let me redraw this maybe a little bit so that it's more clear. I'm gonna draw kind of like a box this time so that we can maybe get a better idea. So I was a little busy over there. I had a lot of stuff. So static just means it's kind of just separate from an instance, and then non-static would be things like this. So we'll say this is J, which is John, and this is D, which is Doe. So the names are non-static. They're in specific objects, but the count out here, whatever it is, that is static. When I call a function, I'll just call it nfunc rather than give it the name that I gave earlier. That's a non-static function. Then it's called from an object. So the way I might call that would be j.nfunc or j.getName is the example we did earlier. In fact, let me just do getName. It has to use an object to call itself, meaning that the function is executing right here. It's executing in the person themselves. And that's why it's able to access both the name, which is non-static, as well as the count. So everybody can see static things, no matter what the scope is, because static things exist just kind of off wherever. They're always accessible, no matter what. I can always see the count as long as I have permission with the whole protected and private and public stuff, but I always have access to it as far as seeing it. There's always a way to see it. Same thing if I was to call d.getName. I should have access to everything that's in the current object, specifically the name, as well as anything that's static. But if I call something from a static scope, which I'll just say off here is an sfunc, a static function, then because it's not tied to a specific object, let's just say get count, it gets called not from any one of these single objects, these circles here, but instead from the static scope. Which means it also has access to static things. It can see things that are in the same area. But if I was to try to access the name from just like this square out here, the static scope, when I say name, do I mean this one or that one? And so you can see there's a little bit of an ambiguity if you try to access something that's non-static from a static scope, because the question becomes, well, what name are you talking about? What non-static object are you talking about when you want the name? We could have hundreds of objects, and it's ambiguous as to which one that belongs to when we actually try to say it. So that's the reason we can't access these. So this is a no, as well as this one. If I was to try and grab the name, it's unclear which one it is if I don't have knowledge of what object it was that called it. In other words, the non-static part of it. Does that make a little bit more sense as to why a static scope can access only static things and a non-static scope can do whatever it wants? And just being the fact that they're tied to an instance, which is not. Cool. Okay. Fair enough. If anybody has any questions, again, just stop me. One last thing to mention about this is to bring up this is in the keyword this. So this is all kind of just abstract so far. We're just talking in terms of like these objects that exist in space and where we can use these in functions. This is inherently a non-static. I don't want to say object, but like variable. So this is always non-static. And that is because this is a keyword that refers to the current calling object. It has to have information about who the caller is in order to be used. So consider when I call the function j.getName, this is j. When I call the function d.getName, this is d. So all objects have, I'll put it back. I know it's a little hard to read. I made things kind of small, but every object has a this when you call it. It's not, again, stored, but when you call a function, it will keep track of who it is that called the function. And because of that, because of the fact that it is always pointing to the object who called a function, it is non-static by definition. It refers to a specific object and it can't just be free floating. So on that note, because it's non-static, something to keep in mind is based off of what we wrote earlier here. The only caveat we had, the only restriction, was that we cannot use non-static variables in a static scope. I couldn't use the name in my getCount function because whose name am I talking about, right, was our problem. In the same regard, I cannot use the word this in a non-static function because of the fact that I don't know what this means. If I was to be out here where this red point is, this non-static point, then I cannot know who this is. Is this J, John, or is this D, Doe? It's unclear. And again, I could have like hundreds of these things. So in non-static scopes is the only time you're allowed to use non-static variables, meaning this and instance variables. Cool. Any final questions on that? Just wanted to kind of clear up a few things, and I know it can be hard to wrap your head around at first. I think this becomes easier to understand as you do more object-oriented programming. Okay, fair enough. Don't see any questions. I apologize that I'm not doing any actually programming here, but I think the concept is more important than the actual programming stuff. Now, there's one more thing I wanted to talk about, which is a new topic. I don't want to get too far into it because it won't be on the first exam, it'll be on the second one. And so I really don't want to start it before the first exam. But I guess I'm just going to talk about it anyways, and then we'll refresh kind of afterwards. But I want to talk a little bit about the idea of recursion, both from a math standpoint and from a computer science standpoint. The computer science standpoint definition is like pretty straightforward. It just means to call a function from itself, but we want to get maybe more of an idea of why that's important from like a math point of view, first off. So first things first, let's just start with something non-recursive and talk about something like factorial. So does anybody remember how to do factorial? Let's just say I do 6 factorial. Does anybody remember what this expands out to, or like how you do this? Actually, for the sake of making your typing easier, let me say that this is 3 factorial. How do I do something like 3 factorial? Right? 3 times 2 times 1. You got it? So I'm just going to kind of make a table here. This is our factorial. We'll expand it a little bit. And then we'll simplify it a little bit. So like you said, this is 3 times 2 times 1. And then so 2 factorial should be 2 times 1. And 1 factorial should be 1. And then we'll just make a note here that 0 factorial is also 1. So just as a refresher, if you don't remember, factorial just means to multiply by all of the numbers below the current one until you hit 1. Except for 0 factorial, which is just defined as 1. That's the only exception to this. So we can see that here we can almost kind of see a pattern in some way. This one is only really different from the one below it in that it has a 3. So if I was to look at this, this is a 3 times 2 times 1, and the 2 times 1 was down here on the previous one, and then I can see kind of that this 1 was on the previous one, and then we have this other one which is like breaks that pattern, right? So this breaks the pattern. And so we'll need to consider it kind of especially when we do this recursively. But the idea here, first off, is that we can have an answer that takes the form of a previous answer in our table. Consider if I was to expand this further and write 4 factorial, then it would be 4 times 3 times 2 times 1. So it would be the one below it in the table, 3 times 2 times 1, times the new number, which is 4. In that way, we could rewrite this, right, to be 3 times 2 factorial. Because this 3 is the current number, and then the 2 factorial is the thing on the previous part of the table. In the same way, I could write 2 factorial as 2 times 1 factorial, and then 1 factorial doesn't have anything below it because we said that 0 breaks the pattern, so it's just 1, and this one is also just 1. So the thing here that we can kind of notice is that for all the numbers 2 and greater, then it's equal to whatever the current number is. Let's just say n. We'll say that this is the n here, times n minus 1, whatever the number that is that comes before the number that we're doing factorial. And then these two are like different, right? So this is just 1. I can't rewrite it in some way that is dependent on other answers. And this one is also just 1. So in that regard, the numbers 2 and higher are dependent on some kind of formula where we can write it explicitly like this. And the other 2 are not dependent on a formula. When we are able to solve something using previous solutions, then in math, that's where recursion comes in. So this part specifically, we'll say, is the recursion. This part specifically, the n minus 1 factorial. It relies on a previous answer that we have inside of the table. When I do 3 factorial, it needs to know what 2 factorial is first in order to be able to solve it. If I do 2 factorial, it needs to know what 1 factorial is before it's able to solve it. So they require some sort of previous knowledge. In that regard, there are recursive cases. The other 2, where we don't have to have any sort of knowledge about a previous result, these are non-recursive. There are base cases. So let's go ahead and just try to write a short program that's able to do this, keeping in mind especially this yellow thing right here. So I'm going to do it without the base cases first, and then I want you guys to kind of pay attention and tell me if I'm doing something wrong. I'm going to write a function. I'm going to call it integer factorial. We'll just do fact to keep it kind of simple. And we're going to have it take an integer n. And what this should do is it should return the result of the factorial of whatever n is. I can actually write this super easily. I can just write return, and then we know that the answer is always n times n minus 1 factorial, right? So I'm able to actually call the function itself and do n minus 1. And then that's that. It's one line and it does factorial. No need for loops. We've actually just done this all with one line in a function. And so hopefully it's clear that this and this are just the same thing, one written in math notation, the other one written with a function. Now, I don't have the base cases. That is going to cause an issue. Can somebody figure out what that is? What what might be my issue if I was to call this in main as just fact4, let's say. Let's say fact3, let's try to keep it small. What's going to be my issue? Am I going to get a wrong answer, or is there going to be a crash, or is there going to be some sort of evaluation error? Any guesses as to what the issue might be if I don't have base cases? Cool. So I got a private response, but you are right. And the response was, will it go on forever? And you're exactly right. So let's just kind of visualize why you're right. If I was to call this as factorial 3, then consider I would go and call the function. N would be equal to 3. I would get down to here, and I would want to do 3 times, so it knows to, I'm just going to put R, 3 times the factorial call on 2, right? Okay, so we go down here, we go to the next function call. So when we get down to this line, it's going to jump back up to the top, because that's just how function calls work, right? They jump around. And we go here, and now it calls it with the parameter n equals 2. And the code says, well, return the value of 2 times the factorial of 1. And so it goes back here and it jumps back up to the top and it tries to execute this code. So it does a function call where it jumps over there again with n equals 1, and it tries to evaluate the expression return n, which is 1, times the factorial of 0, which is n minus 1. Okay, so it jumps back up to the top again, and you can probably see where this is going. It's going to call it for 1 times f of 0, and then 0 times f of negative 1, which first off we know is not the right answer anyways, because that would give us 0. 0 times anything is 0, and this would kind of like multiply its way back up. So we have an issue here, in that it's going to keep counting downwards. This minus 1 is going to keep calling it so that it first calls it 3, and then 2, and then 1, and 0. And it goes on unbounded until it either overflows, which probably not, or it runs out of memory because it has too many function calls going on and it just crashes, which is called a stack overflow. So when we get to recursive programming, you're probably going to have some stack overflows when you first do it. And if you've ever been on the website, that's where the name comes from. It's because you did too many function calls, generally is why the stack overflows. And so recursion is a very easy way to stack overflow. So this will loop infinitely. In that regard, we need these base cases as a stopping point to tell us that that's a definition of something where we can now use it to solve it. So in order to fill in this 1 factorial, which is needed by this 2 factorial, which would be needed higher up on the 3 factorial, we need to know what 1 factorial is. So we need something to be defined in the context of our math problem where we can use it as a stopping point for our problem. And that's exactly what base cases are. Then just for the future, they don't have to be mathematically related. We can do this with things like pointers, which we'll probably do an example of. But we need some sort of stopping point, and that's our base cases. You can have any number of base cases, just as the thing to mention. In fact, I could arbitrarily say that 2 factorial is 2 and make that my base case as well. And I could say 3 factorial is 6 and make that a base case as well, which would be a little strange, but it's kind of like a cutoff point that you want to be a stopping point. And you can make it anywhere, but I think for the sake of practice, it's usually good to make it something that's simple and can't be defined in terms of anything else. And in that way, I'm going to use 1 factorial and 0 factorial both. You could totally make just 0 factorial work for this specific example, but I'm going to argue that we'll do both. So in order to do that, you're going to need to check some sort of condition. So we're just going to check if n is 0 or if n is 1. And we will, in that case, return 1. So now if we go back to our call order here, we'll be started with a 3. It's going to start at the top with n equals 3. It's going to check, is that 0 or 1? It's not. And so it will try to find the recursion version of it. It will try to recurse. and it will say, okay, well, I'm going to return 3 times the result of factorial of 2. Jumps back up to the top, checks, is n equal to 0 or 1? No, it's 2, so that's okay. We'll try to do the next case, which is 2 times the factorial of 1. And it will go down there, and it will say n is equal to 1, and it matches this, and now it returns 1. So we've stopped ourselves from recursing any further. So it acts as a stopping point that stops us from looping forever. And now if we were to go back here, it's going to work its way back up the stack. So now we know when n equals 1, it's just going to return 1, which means that this one, if it was returning 2 times the factorial of 1, it now knows that this factorial of 1 evaluates to 1, and so it returns 2. And then we go back up to here, and whereas this one was going to return the value of 3 times 2 factorial, and we call it with 2, it now knows that that is 2, because that was the return value here. So the return value gets kind of like plugged in and feeds its way back up this stack of calls that we have here. Which is something to keep in mind, just like that technical implementation. But if you keep in mind like the math sort of thing, where we're doing this as some sort of explicit formula of some kind and just writing it as a function call in our program, then it should work out okay. So definitely don't overthink it, even if I'm going into more detail here. Does everybody kind of get this concept that it relies on a previous answer? And in programming, the way we can do that is we can have it get that answer with a function call and just have it refer to itself. So in the context of programming languages, recursion just means that a function calls itself. It's really that simple. The definition's not too complex. But in terms of math and like problem solving, it refers to using a previous solution to come up with a solution to your current problem. We got 2 minutes left, but I think that's probably a good stopping point. We'll talk more about recursion maybe on Thursday, and then definitely after the exam we'll try to review on it a little bit. We're kind of in a weird place just because of the holidays. So okay, I guess on that note, I will stick around if anybody has any questions. I'm going to try to put up a list of topics for the exam so that everybody knows what to study. And then on Tuesday, we're going to do review. And then on Thursday is going to be the actual exam. So please think about if you have any questions in particular, and feel free to come in and ask it, and we'll try to go over that. If not, we'll just review all the topics. So I guess I will see everybody Thursday then.